Okay, so I'll introduce Cython. I'll show you an example how to use Cython. And I will also show you how you can use Cython with NumPy, and then give you a summary. So here we go. So Cython is a superset of Python, which means that any normal Python program is also a valid Cython program. But a Cython program, you can have you have access to additional keywords that you can use. Okay? So in these additional keywords, they give you functionality for specifying the types of your variables that you use. And it also allows you to call C functions. And then internally, what happens is that when you compile your Cython program, Cython will generate the C wrapper code and then compile it into a Python extension module. And you can, after you've compiled it, you can just import your module in a normal Python program and use these functions just as well as if they were implemented in normal Python. So from a user perspective, the module is just like any other Python module, but with the advantage that you get potentially the speed-ups of C. And the big advantage of using this approach is that we can start with a normal Python implementation, because Cython is just normal Python. Any Python program is also a valid Cython program. And then we can start adding types and all these optimizations that Cython adds up, provides us incrementally, and basically make our program faster and faster over time. And so one of the most important keywords that you get in Cython is the cdef. And so the cdef is used to declare the type of your variable. And so for example here, in the first line, we create 3 variables of type integers. Right? So these are now C variables of types integers with the name I, j, and k. In the next line, we create, again, C variables of type float. And we create a floating value, then we create an array. And here we create actually a pointer to a float, which is a concept that is used in the C language. So this is how we can define. So here I showed you how we can define the types of variables. Now I can show you how you can specify the types in functions. And so there are basically 3 different ways how you can specify types and functions. The first one, so obviously you can just write a normal function, Python function. That's also a valid Cython function. But also, we can start specifying the type of our variables inside the definition here. So here, I create a Cython function where I specify that the first argument is of type int, and the second argument is a pointer to a character, which is here used for strings. So this is a Python function where we've specified the types of the arguments. So, and for this, we just use the normal def. We can also use cdef, and what happens is that we can also specify the output value of the return value of our function. So now here, x returns an integer. Right? And the Cython compiler can make use of the fact that we know that x will always return integers. And it will take in an integer and a float as the 2 arguments. If you use cdef, then Cython will compile this function into a C function. And it will only be accessible within your Cython module. And it will not be accessible as part of the compiled module. Right? So if you compile this file here, then you will not be able to, you will be able to access foo, but you will not be able to access x because it's a pure C implementation that is not exposed through the Python module. There's also the cpdef, and that's basically hybrid between the first 2. This now generates a C and a Python function of foo2 here. And so now we specify all the types, and we will be able to use the C-compiled, the benefits of the C-compiled implementation of this function, but also it will be made available for the Python module. And yeah, as I noted here, we can specify the types both in the input arguments and the output arguments of these functions. Yeah?
Can C def support complex variables like in C?
I would guess so. I haven't tried it, but just try it out. I don't see a reason why it wouldn't. Okay, so what happens now if we take such a file and compile it? If we don't specify any types in function arguments or also in any variables, then the default will be it will just default to a normal Python object. So basically exactly the behavior that we had with a normal Python implementation. So for example, if I have a loop here for I in range n, if this integer I here, if this I variable here was defined as a normal Python variable, then we will end up with a normal Python loop here. But if I was defined to be a C variable of type integer, then Cython can automatically compile this and optimize this into its normal standard C loop. Okay, and this is where the benefit comes from. So by specifying these types here, we can suddenly convert normal Python loops into C loops, which can be optimized by our C compiler. So let's look at a concrete example to give you an idea how this is being used in practice. So imagine we wanted to compute the integral of a function. Right? So here's our function. It's sine x squared. So it starts with the sinus, and then the frequency becomes faster and faster. And we would like to integrate, basically compute the area underneath that function. And the way we do that is we will evaluate the function at each point, and then we will break up this entire line into segments, and then always evaluate the function at one point and multiply it by the width of the segment, and then add it all up. Right? So and then you end up with an approximation that is shown here in this green. So you always get these bars. And you just we know the volume of the area of a bar, and we just sum up all these areas of these bars. And then with that, we approximate the integral of the function. So the point here now is that for numerical integration like that, the accuracy of the integration increases with the number of intervals. Right? So ideally, we would like to have as many intervals here as possible to get an accurate solution. So as long as we're doing just 1D integrals, we might be fine with our Python loop. But if we're now integrating 3D functions, then very quickly we will hit a speed limit. So here's a Cython example of this. Here's a Python example of this, so a non-optimized version of the integration. The way it works is that, well, first we need to define our integrand. So this is just sine of x squared. This is the function that we want to integrate. And then we write this function called integrate f that takes in the starting point and the end point where we want to integrate and the number of intervals that we use. And so the way it works now is that we have S will be the sum of the area. Initially will be 0. Then we define a step size for our segments. So this in this case is just b minus a divided by n. Right? This is how many how wide our interval is. Then we loop over all the number of segments that we have and evaluate the function at a plus I times dx. So evaluate the function at the point where the segment starts and add it to S. And before we return it, we also multiply it by the width of the segments. So this is a simple function that integrates us now our f, or approximates the integration, the integral of our f. So if I run this with n equals, how much is that, 1 million, it takes about 3.5 seconds. Okay, so here we go. So now I can obviously run this as a normal Python program, but I want to use Cython. So what I do is I save this file not as a py file, but as integral.pyx. But I keep the implementation exactly as it is. Okay? And the reason why I can do that is because Python is also legal Cython code. And so now I need to compile this file. And the way I do that is I call Cython integral.pyx, and this will generate a C file. It will generate a C implementation of my integral, and which will be called integral.c, so you can actually open it and inspect it. And then you can call the compiler GCC I used here. This is a C compiler. So with some arguments here, they're not too important, integral.c. So basically I'm compiling now my program, and with the second line, I make a module out of it so that I can load it up in Python. So this is how you would compile it manually. There's actually a much more convenient way of compiling it, and that is with distutils. And so you've learned this before with the modules. We can write the setup.py file. And so basically, this is a normal setup.py file, except that I also import this Cython.distutils. And that allows me to, in my setup routine, I can provide these X modules where I specify extensions, and I can also add pyx files in here. So I just create a setup file where I list up all my pyx files that I'm interested in. And then I can call Python setup.py build ext -- in place, and that will automatically Cythonize my pyx file and compile it and generate the shared module so that I can load it up. Okay, so do I have a working example? No. Yeah. Okay, so now we can go ahead and start. So far, nothing has changed, right? We've compiled now. We have a normal Python implementation, and we just use it in Cython rather than normal Python. But so since we're now in Cython, now we can start adding types. So as I said, so simply compiling the Cython files gives only minor speed up. So maybe the loop runs in C, but makes various calls to the Python C API. So really, to get now the full speed up, we need to add types to our program. And this is what I've done here. So for a start, I kept the f function here the same, and I only added types to our integrate f function here. And so, okay, what do we have? So we know that our starting point A is a double, so I can specify the type here. We know that our end integration point is also double, I can specify that here. And the number of intervals is an integer, so I can specify int here. And the result will be a double function as well, a double variable. And since we want to call integrate f from Python, I use cpdef here, so that we get both a C and a Python implementation. And so basically now what I'm doing is I just go through all the lines in my program, and whenever I create a new variable, I specify also its type. So I know s is of type double, dx is of type double, int I is of type int, and so on. And that's the only changes that I've made. And so now I can even, this is right, I'm going to show you an example in a second. So this I call the semi-Python version, because it only specifies the types for integrate f, but not for f. So here I kept my f exactly the same. The full version, the fully typed version here, also, now everything is the same. It's only that I also specify the types for this function f here. Okay? And so now the trick is that the difference is before. So here, see, I use a cdef. So this is now a pure C implementation. And in the integrate f function in here, this f doesn't need to launch out to Python anymore. But we can call directly the C implementation. And that's why this is why this implementation is so much faster than the one before. Or I will show you that it's faster. It's because now this f calls can happen directly in C. While my previous implementation, here, this f was still a Python object. So when I called f down here, it had to launch out to Python, call this function here, and then get its return value. So this is the fully typed version. As you can see now, for every line I've specified, or for every variable that I use, and every function that I use, I now specified the types. And if I run this now, we get a 10 times speed up. So I'll show this to you. Let's go to code snippets. Mixed. Cython. Okay, so here we have, I've downloaded the code snippets, and you have the 3 implementations here now. Integral.py.pyx is a pure Python implementation, so there I haven't specified any types. Then I have this integral semi-py, so there I specified types except for this f function. And finally, I have integral.pyx, and that's the fully typed version. Okay? And then I have the setup file that we can now use to compile our program. And then I also have this test.py. And what that does, it basically just loads in all these 3 different modules and then calls them on quite a large n number. And then also down here does some time it, just calls them through time it so that we can see how long time is being spent in each of the implementations. So all this code is part of the code snippet, so you can run it. I also have this README file here that tells you what you need to do to run it. So let's first compile the modules. So I call python setup.py. Okay, so you need to install Cython, of course. Okay, there we go. So now I've got my modules compiled, and you can see that we have now these .so files, and these are the compiled modules. Okay, these are the ones that when we import now the modules, these are the objects that we're actually using. And you can see that we have one for integral pi. This is the one where we didn't specify any types, and then also the integral semi-pi, where we partly use types. And so now I can run test.py. And well, the first important thing is that we have a pure Python integrate, a semi-Cython integrate, and a Cython integrate, and they all return the same value, right? So that's something that we should check, that just changing the implementation should have not changed the return value that we get out. So that's always something useful that you should check. And then finally, so the second part shows you how much time the different implementations took. So I repeated the experiment 10 times so that we can, and I think I took the minimum. And so, okay, so we can see the pure Python integrate takes about 3.4 seconds. Then the semi-CPython integration takes about 2 seconds. So this is the one where I specify types everywhere except for the f, right? And so you can see the speed up there's a speed up, but it's actually not that significant. really the huge speed up we get when we switch to the fully Cython version, where we change the f function to being a pure c function. Right, so then suddenly we go from 3.4 seconds to 0.4 seconds, so, which is exactly the 10 times speed up that I mentioned before. Okay, are there any questions regarding Cython? So there's also, yeah. So I have a few more slides on NumPy with Cython, but it works very similar. So these are just some timings. But so basically, you can do exactly the same way what we've done now, also with NumPy arrays. So, for example, here we have a simple function that just takes in an array and it computes the sinus, element-wise, the sinus of each element of the array. Right? So we could vectorize this, of course, but here I've just written out the loop again. And so the way I can use that is I create a new array, and I call apply sinus on this array, and I get a new array back where each value here will be the sinus version of it will be the sinus evaluation of the element of A. So now what I can do is I can create NumPy data types. So this is how I create so I use cdef again, and I specify, okay, my out variable will be a NumPy ND array of type ND type double, and it will be one-dimensional. Okay? So I first specify the type of the NumPy array, and then I can create it. So here I can say out equals numpy.zeros, 1,000 of length 1,000, and then the D type, obviously, it has to match up. So if I use double here, then when I create the array, it also has to be double. And so there's actually you can't see this here, but there's a mapping here, but it's not exactly the same type that you need to use. But you need to use this translation table here. So when you use double in numpy.zeros, you will use double, but in the Cython data type, you have to use double underscore t, and the underscore you can't see here. But actually up here, I typed in double underscore t. If you download the notebooks, you will see it. And so now I can go ahead and do exactly what I've done before and declare the NumPy data types for my implementation. It looks a bit messy first, but I mean, it's not that complicated. So this is the function definition. So this is my apply sign. And you can see that it takes in an array A with the name A. It's an ND array of type double, and it's got a one-dimensional. And the output will also be an ND array of type double with one dimensions, with shape 1. Then I create an integer, and I create the output array exactly the same way. And then the actual loop down here is unchanged, right? And then the way you can use it is you save this file as pyx, you compile it, and then you can import it. Or you can write from apply, import apply sign, and then just create a new NumPy array. So this is now, from the user's perspective, you don't actually see anymore that there was any Cython involved, right? This is just now called as if it was a normal Python module. And now if we do the timings again, so the pure Python implementation of this is, again, normalized 1. Then the Cython implementation that I've just shown you takes 0.205 seconds. And so interestingly, I've also tried out a NumPy vectorized version. And then actually, it turns out that this one is the fastest. So this one takes 0.202 seconds. So it's a lesson learned. NumPy vectorization can actually be also faster than at least the Cython implementations. But they're very close. Okay, so Cython summary. So as advantages, right? Big advantage is that we can start with an existing Python implementation, and we can just incrementally start optimizing it. And so the generated code that Cython generates is often more compact and more readable in Swig if you have to debug it. It's got quite an active developer community, and it is fairly advanced and flexible. There are some downsides. So in some cases, it's not as fast as, for example, instant in certain loops. It's not as suitable if you have large libraries that you want to wrap. So imagine if you have a big system and you have to add in all the types, it becomes quite messy. And the fully optimized code, as you saw in the previous examples, sometimes not that readable because you have these types flying all around. But at least for smaller programs, it should be maybe considered as one of the first choices if you want to mix Python and C. And so just as a reminder again, so these examples, I think they're a really good starting point for these different tools. And as I mentioned, there's examples for instance and for Swig and for Cython. OK, any questions? Everyone clear for the assignment 4 to implement the Cython? Maybe? OK, then have fun.